The first thing we need to look at with the periodic table is some basic features of it in terms of how it's laid out, what it shows us, and a little bit of the history of how it was developed. So the first thing to realise is the periodic table is just a way of arranging the elements in a very kind of logical and useful way for scientists to use. So the first question is to make sure that you're clear on is you have to know what an element actually is. So an element is just defined as a substance containing only one type of atom that cannot be broken down into simpler substances by chemical means. What that basically means is if I was describing the element carbon to you, what I basically would be meaning by that is in a lump of carbon, there's only one type of atom in there, which is a carbon atom, and I can't make that any simpler. So carbon is as basic as it goes. If I had lithium, a lithium atom is as simple as lithium goes. You can't get it any simpler than the atoms you've got. So the periodic table is just a way of arranging those elements in a way that makes sense. So the basic shape looks like this, where each element is given its own box within the table. Now, the basic features of this should be familiar to you, but just to recap them. The vertical columns you've got across the periodic table are known as groups, and the horizontal rows are known as periods. You are meant to know the names of some specific groups, so you should know that group 1 is known as the alkali metals, group 2 is known as the alkaline earth metals, the block in the middle isn't really a group but it's known as the transition metals, then group 7 is known as the halogens, and group 0 is known as the noble gases. The key feature about groups in our modern periodic table, which makes them in the same group, is that they have the same number of outer shell electrons. In other words, an element which is found in group 1 must have one electron in its outer shell. Now, in terms of the locations of different elements within the periodic table, what we should know is that all the metals are found on the left-hand side. There's a staircase going halfway across the right-hand side of the periodic table, which divides your metals from your non-metals. So the metals are to the left-hand side, the non-metals are to the right-hand side. You're meant to know the states in terms of solid, liquid, gas of some distinctive elements. Most of the elements, the vast majority, are solids at room temperature. There are only 2 liquid elements in the whole periodic table. And those 2 elements are bromine in group 7 and mercury in the transition metals. Remember, mercury is used in those thermometers. It's a liquid metal. So you have to remember that they are the only 2 liquid elements at room temperature. A few more are gases. So the gases we have are the entire noble gas group, group 0, the top 2 halogens, so that's fluorine and chlorine, and then also along this second period you've got nitrogen and oxygen, as well as hydrogen up in its own little box there. So they're the gaseous elements, gases at room temperature. You've got your 2 liquid elements, and all the other elements in the periodic table are solids at room temperature. Now, the scientist who was key in developing this periodic table was a Russian scientist called Dmitry Mendeleev. What you're meant to know is 3 key features about his periodic table, which is a little bit different to ours, as well as 3 contrasting features, or 3 or 4 contrasting features of our modern periodic table. So the 3 key features of Mendeleev's periodic table is that he ordered them in terms of atomic mass. So the lightest elements were up in the top, and as you went further across and further down, they got heavier and heavier. He put elements in groups, and he arranged those groups in terms of properties. So elements he saw that had similar properties went in the same group. And the key thing that Mendeleev did that made him quite clever and sort of stand out against other people who were trying to arrange the elements was that he didn't assume that they discovered all the elements at that point. He left gaps where he thought that more elements would be discovered to fill the gaps in. There are a couple of key features about our modern periodic table are different to Mendeleev's. The key difference is that the ordering is a little bit different. We don't use atomic mass for ordering now, we use a slightly better number, the atomic number, basically the number of protons. There are no longer any gaps, so in other words all the elements have now been discovered, or all the common ones have been discovered. The noble gases weren't around or weren't discovered when Mendeleev was making his table. We've now discovered this group, so they're now found on the right hand side. And Mendeleev did have some transition metals in his periodic table, but he didn't really know where to put them. So nowadays we have them in their own little block in the centre of the periodic table, right here. So the rest of the periodic table topic looks at individual groups or sections of this table and identifies some key features of the elements. So the groups we have to look at are group 1, the alkali metals, group 7, the halogens, group 0, the noble gases, as well as a little bit on the transition metals. So group 1 is known as the alkali metals. So you've got lithium, sodium, potassium, rubidium and cesium. In terms of some basic features or basic properties of them, we've got these. So they are low density metals. They'll float on water, whereas most other metals in the periodic table will sink in water. They're easily cut. Again, most metals are quite hard, are quite resistant to cutting, but the group 1 metals you can cut quite easily with a sharp knife. And then finally, they're quite shiny metals, but they'll react very quickly with air and do what's called tarnishing, where they turn dull. There's one main reaction of the group bond metals we're meant to know about, which is a reaction with water. So the reaction with water is an experiment you should remember seeing in class. It involves a big trough of water behind the safety screen where you cut up little bits of metal, remove some oil from them and then drop them into water. First thing you need to know about is some key safety features. Now the group bond metals are stored normally in a little jar full of oil because if they react with air or water they'll react very quickly. By the same kind of token, you don't want to touch them with your hands because equally your hands could have water on them. So we pick them up with tweezers. We use a safety screen for the reaction because the metal can actually jump out and go towards you, so the safety screen prevents that from happening. You'd obviously wear safety glasses for the same reason, and we use a large volume of water just so it doesn't get too hot, too reactive in a confined space and could potentially crack, for example, a beaker. So we use a large trough. The reaction itself is fairly simple in terms of what's made. Your group bond metal will react with water and makes a compound known as a metal hydroxide with hydrogen given off as a byproduct. So whenever you see hydrogen being produced, it's always going to be observed by a gas being formed or like bubbles being produced. In terms of an example of a symbol equation for that, if we take the example of potassium symbol is K, so we have K for the metal. Water is a common compound, it's H2O. Now for the metal hydroxide, we're going to make potassium hydroxide here. We need to do a swap and drop to work out the formula of the hydroxide. That involves using K, which is in group 1 of the periodic table, so it's going to be K plus in the compound. Hydroxide is found on the back of your periodic table because it's not an element, it's a molecular ion. It's OH minus. So 1 plus 1 minus swapped and dropped over will give us KOH. Hydrogen is just H, but the diatomic gas has to be H2. Then we see the balances equation. We need to make the hydrogens balance. There's 2 on this side, but 3 on this side. I'm going to double the KOH to make 4 hydrogens, and then double this to make 4 as well. That makes the oxygens balanced again, but just need to make sure my potassiums are balanced. Need a 2 here as well. So that's the reaction or the equation. We also need to know some observations about what we'd see for 3 of the alkali metals, lithium, sodium and potassium. So with lithium, there's a number of observations you can rely on. It's going to move about in the surface because remember lithium floats as do all the group bond metals and will move about because it's quite an energetic reaction. The bubbles produced come from the hydrogen you've got in the equation. It's a very exothermic heat releasing reaction. The metal eventually will get used up and completely turned into the hydroxide, so it will disappear. And the metal hydroxide is often modeled as a colourless solution. So any of these observations is valid for lithium. Now for sodium, most of these observations will be identical, but because sodium is a little bit more reactive, there's an extra one you need to note down as well. So in addition to all these previous observations, sodium will also melt into a ball because it's quite an even hotter reaction. You actually go past the melting point of sodium in terms of temperature, causing it to melt actually into a little sphere of liquid sodium. Potassium similarly has all these observations, but a couple of extra ones because it's even more reactive. Essentially, potassium is so reactive that the hydrogen produced in the reaction ignites or goes on fire, and we see a nice potassium lilac flame as well as crackling from the hydrogen kind of exploding. Now, one thing from those observations that we can tell quite clearly is that as you go down group 1, so lithium's at the top, then sodium, potassium, you get more and more reactive. So that's the last little thing you need to be able to explain about the group 1 metals. So the first thing to realise is that when you're reacting a group 1 metal with anything, even if it's just like water we have up here, it's going to be losing an electron. So how do we see that? If we look at the start, the symbol for potassium here is just K, but when it forms potassium hydroxide, yes, it doesn't look like there's a charge there, but if we think about how we made our swap and drop, we're basically saying it's turned into K plus and it's doing an ionic bond with a negative ion. So if we just separate that out and just show the potassium, so this is known as a half equation when you're only showing one element by itself. It's starting off as K, the metal, potassium, and it's turning into K plus. How that happens is it has to lose an electron. It's not too difficult to see why it wants to lose an electron. The electronic configuration of potassium is 2881. It's got 1 electron inside the shell, which is true for all the group 1 metals. To get a full outer shell, it wants to lose that outer electron. And to lose that outer electron will give it a full outer shell and leave you with a positive ion. So the difference between the reactivity of all the group 1 metals is basically that they all want to lose that outer electron. It's just a case of how easy they are to do that. Okay. What's going to affect how easy it is for them to lose that outer electron is their size. The smallest group 1 metal is lithium, and in its case, its outer electron is very, very close to the nucleus. But as you go further and further down, as you add more and more shells, the outer electron becomes further and further away from the nucleus which is holding it in. Therefore it's much more easy to lose the electron, and therefore it's a much more reactive element. So to repeat that, it's easier for you to lose an outer shell electron as you go down group 1. So lithium quite hard, then sodium easier, potassium even easier still. The reason is that the elements are getting bigger, there's more shells, therefore the outer electron, this one I have in the outer shell, is getting further and further away from the middle of the nucleus. It means it's more attracted to the nucleus, therefore harder to lose, and therefore the reactivity will easier to lose, therefore the reactivity will increase as you go further and further down the group. So the next group we have to focus on is the halogens, which are found in group 7. So the most common halogens you'll hear about are from the top of the group, fluorine, followed by chlorine, bromine and iodine. In terms of key features shared by all of them, they're all toxic elements, they're poisonous to humans, and they're all diatomic. And as a reminder of what diatomic means, it means it's when you've got two atoms covalently bonded within a molecule. Remember, covalent bonding is for non-metals. Group 7 is on the right side of the periodic table, so they're all non-metals, and two of them join together to make a molecule. It's known as diatomic. So what that looks like is when you have chlorine, for example, the element, it'll never exist as a single chlorine atom. It always comes around in pairs. So it'll always be Cl2 for the formula, like F2I2Br2 for the other ones as well. You have to know about the appearances of these halogens, first of all when they're just a normal element, and also when you dissolve them in water. So from top to bottom, fluorine looks like a yellow gas, chlorine looks like a yellow-green gas, bromine looks like a red-brown liquid, and iodine looks like a grey-black solid. Now whenever you dissolve them in water to make a solution, we don't have one for fluorine because fluorine is actually too reactive. It would actually explode when it goes in contact with water, so we only have observations for chlorine, bromine and iodine. Chlorine dissolved in water makes a pale green solution, bromine dissolved in water makes an orange solution, and iodine dissolved in water makes a brown solution. Next thing is you have to know a couple of wee kind of bonus facts about two of the elements. You know an observation for the sublimation of iodine and also a test for chlorine. So iodine first. So iodine has this unusual property where it will sublime, which not many substances do. Sublimation as a process is when you go directly from solid to gas when you heat it up, but you don't go to liquid in between. So you think of water, you go from an ice cube to liquid water to steam. That's two different steps. If you heat up solid iodine, it goes directly to gas. You just need to know the observation for that. And as the iodine starts off as a grey-black solid and it turns into a purple gas whenever it sublimes. The next fact is about chlorine. There is a chemical test that allows you to work out if you've got chlorine gas present. The test is that you use a piece of damp universal indicator paper, so you dampen it with a bit of water. If you hold that over chlorine gas, it's first going to turn red as if it was an acid, but then it's going to bleach white because chlorine also acts a little bit like a bleach. In the same way that we had a distinctive reaction of the group 1 metals, which is them reacting with water, we've also got a distinctive reaction for the group 7 elements, the halogens, which is known as a displacement reaction. This is where the halogens react with each other. So in a displacement reaction, you've got two different halogens. One of them will be by himself, like as an element. The other one will be found in a compound. The pattern we see is that the more reactive halogen is able to displace, which means push out the less reactive halogen from its compound. It's easier to see that when you actually look at the proper equation, for example. So if we look here, we see we've got chlorine, a halogen by itself as an element, and we also see iodine, another halogen, but it's found within a compound bonded to potassium, so potassium iodide. Between these two, chlorine is the more reactive element, so the reactivity of the halogen decreases down the group, so chlorine's further above iodine makes it more reactive. According to this rule about displacement reactions, a more reactive halogen is able to displace or push out a less reactive halogen from its compound. What that would look like is the chlorine takes the place of the iodine in the compound with potassium, so we form KCl as opposed to Ki, and iodine is pushed out by itself. Need to be careful with things like diatomic elements, so chlorine and iodine are both diatomic, so have to be Cl2 and I2. And to balance the equation we need 2's in front of the potassium iodide and the potassium chloride. You also need to know about the observation for that reaction, which looks like this. So how the reaction normally works is that you have the compound dissolved in water. So potassium iodide is just like salt. It's dissolved in water. It's going to start off as a colourless solution. You will add your chlorine to that solution, and that will cause the displacement reaction to take place, which causes you to form potassium chloride, which is also a colourless solution, but you form iodine in that container as well. Iodine, as we learned about when dissolved in water, is a brown solution, so the colour change will be colourless to brown in this case. So the way we work out what the colour change is going to be, it generally will start off being colourless, And depending on which halogen is being produced in solution, so for example, if you made bromine in solution, the colour change will be going to orange. In this case, making iodine, so it's a brown solution formed. The last thing you're meant to know about the halogens is again the trend in reactivity, like we saw at group 1. The trend in reactivity of the halogens is opposite to group 1. Group 1 got more reactive down the group, the halogens get less reactive down the group. The difference in reactivity is that the halogens actually want to gain an electron to get a full outer shell, whereas with the group 1 metals they want to lose an electron to get the full outer shell. If you think about how easy it is to gain an electron, you need a strong attraction between your electron, which is coming into your atom, and the nucleus. As you go down group 7, the atoms get bigger and bigger and bigger. Therefore, an electron is coming in to join the atom doesn't feel as attracted to the nucleus at the bottom of the group as it does at the top of the group. So in other words, fluorine, which is really small, will feel a really strong attraction to an incoming electron, but iodine, which is really big, will not pull that electron in very strongly, which makes it less reactive. We see this again in the half equation. Chlorine wants again an electron, but remember chlorine is diatomic, so you need 2 electrons with 2 chlorines to form 2Cl-. So again, our explanation for that is that as you go down the group, the atoms get bigger, and therefore the incoming electron is further away from the nucleus, so it's not pulled in as strongly, makes the reactivity less. There's 2 more small groups we need to look at in the periodic table. The first one is noble gases. This is a very small little section. You just need to know 3 main facts about the noble gases. Noble gases are famous for being very, very unreactive. The reason that they're unreactive is that they already have a full outer shell. They don't need to gain or lose any electrons to get that full outer shell. They won't basically react with anything. Second key fact is that they're colourless gases. And finally, there's one little trend you need to know about. They are all gases, but as you go down the group from top to bottom, the boiling point does actually increase a wee bit. So the boiling point increases as you go down the group. The final thing we need to know about in the periodic table topic is the transition metals. We need a couple of facts about this block in the middle of the periodic table. So we've already looked at a group of metals in the periodic table, just group 1. Transition metals are very different to group 1 elements. They've got a lot of contrast with them. In comparison to the group 1 metals, the transition metals have a higher melting point than group 1. They're more dense than group 1 metals. They're less reactive than group 1 metals. They form a range of ions. What that means is, if you compare that to group 1 metals always form just a 1+ ion. Something that's key about the transition metals is that often they can form a range. So for example, iron can exist as iron 2+, or can also exist as iron 3+. It's got a bit more flexibility there. And the final fact is that whilst the group 1 compounds are always colourless or in solution or white solids, generally if you form a compound with a transition metal, it ends up being coloured. You're meant to know a few specific colours of some transition metal compounds, specifically for copper. So copper oxide is a compound which is a black powder, copper carbonate is a compound which is a green powder, and copper sulfate, when it's hydrated, is a compound which is a blue powder. Again, that's in contrast with the group 1 compounds, which are normally white powders or colourless in solution.